So earlier in the pre-lecture, we looked at gradient descent, just a vanilla version, and we're just going to modify it to say it's batch gradient. So I'm just adding a modifier here. Batch means that we look at all of the examples in the X matrix all together to calculate the correct gradient of the cost function. So here's our cost function. Usually it's going to be an average of some point-wise cost function here. It could be something like this one that we learned specifically for logistic regression. And what we're going to do is we're going to take the gradient of this cost function, and we're going to take small steps, not too big, depending on the slope of the gradient, in the negative direction, right? So slope is usually positive, meaning climbing up, but because we want to minimize the cost, we're going to go in the negative direction. So we're going to calculate the gradient, and then take a learning rate, times it by the gradient at a specific time point where we have weight vector that's going to be changed. So we're going to compute a delta of that weight vector and add it to the weight vector itself to get a new update, right? And the important thing here is that when you look at this specific term, this is the true gradient of the cost function. It's based on a calculation of all of the examples in our training data. So, is there a way that we can speed things up? Well, it turns out there's a really simple and very effective way to do that, and that is called stochastic gradient descent, or SGD, a very popular algorithm in Singapore, right? I'm just kidding. Okay, so what is it? It's basically the idea that we have gradient descent, which goes over all of the examples, but we also have the idea that we're going to look at individual examples, sort of like what PLA does, right? So PLA goes through the data set, selects a misclassified example, and updates its weights accordingly. Okay, so what we're going to do is very similar. We're going to pick one data point in our large matrix X. So we're going to call this point like this one. It's going to be inside of our XY, our whole data set. And we're going to just look at the gradient on that single point. So we're going to calculate the point-wise loss and the gradient with respect to that. And we're going to use that particular point to decide which direction to descend. Now you might be thinking this sounds like a terrible idea, right? What happens if I select a training example that leads me up the hill because the gradient for that specific point points the wrong way? Well, yeah, you'd be right. We'd be stepping in the wrong direction. But think of it in a limit. When we are talking about the average direction, because we're going to pick one of these at any one point in time, we might just randomly pick a point. In the limit, what are we going to get? We're going to be taking an average over all of the data points, and that means the direction that we're descending at in the limit will be the same as the average. Isn't that nice? So what we're saying is we're going to pick a point, okay, x, y. We're going to calculate the gradient with respect to that particular point, and because we're looking at picking the point randomly over the data set, could be any of the total of m examples over the average, and that's going to be the same as the actual gradient. Isn't that nice? So if you have a huge amount of trading data, that's really good, right? You can just say, I'm just going to pick one of all of these m examples and then iterate over many single iterations where you're calculating the gradient on a single point and making optimizations on that. And this is called stochastic gradient descent, SGD. So there are some really important benefits of SGD as we've already gone through. This is the main speed up, okay? It also, because of the fact that it doesn't go on the actual cost manifold, it can help escape local minimum. We might, for example, be over here, right, in this space of possibly different values of theta. Again, let's think about the univariate case where we'll have a cost function here, j, a particular parameter value for theta. When we have a randomized function, we might, go down in this way for a while and get stuck here. But because it's randomized, we're not necessarily going to be stuck. We might go up a bit, might go down a bit, and then after a while, we'll be able to get out of these local minimum, right? So you might see ourselves going down this way and then back up, and then finally converging to a point where it seems to do the best. We can use something like a pocket algorithm to keep the point which we have so far that's lowest and terminate when we have a sufficient number of iterations. And this algorithm is really, really simple. That's really, really helpful to make things work quickly. We also talked about the cost manifold itself having some cases where this type of function here might be actually quite flat. So let me draw that out. Theta here, cost function, and I'll have periods like that, where in the real loss function it looks like this. So let's say we're at this point here, we pick a random example. And the random example might actually have a little bit different type of cost function because it's just for a single point. Then maybe the gradient is in this direction, so I might descend a little bit this way. And later on, if I pick another point from here, it might go like this. So I might go up a little bit this way. Okay, so you can see what's happening with the randomization is that we won't get stuck on a plateau because every single point that we're choosing is going to move us a little bit forward, backward. It's just going to induce some type of random motion on our theta. And then hopefully we'll get to the point where, okay, it's clear that the majority of the points that we pick are going to help us go down the cost function. Okay, so that's really nice. It helps us get out of local minimum. It helps us get across plateaus, and it's incredibly cheap. It doesn't have anything to do with the size of the data set. So usually we use SGD combined with a learning rate, and you can do experiments to decide what type of learning rate to set, but sometimes we'll just use a rule of thumb and make sure our learning rate is not too high so that we don't get this case of bouncing back and forth. Usually we'll start off with a conservative number and see whether we can pump that up without having too many convergence problems. So here's what it looks like. If we do standard gradient descent where we're going through all of the M examples, we can do 10 steps over a large data set and we'll converge to a point like over here, starting from someplace here. But we can do much faster, right? If we have just 10 points in total, right, and we do 30 steps, this is still saving us the cost because 10 steps times 10 examples would give us 100 steps, right? But I can get even farther down the plane. You can see contrasting against the other one, against this one. You can see we're closer to the minimum here, even though we started off on the same point, by making approximately 1/3 of the costs of computation.